Let's now look at some of the important components present in crane construction. Here we see a derrick crane. This is a diagram of the components of a derrick crane. This is a typical plain cog drive slewing mechanism seen on the derrick crane. Jib cranes have similar components. The platform needs to be a rigid foundation or deck upon which the other components may be arranged. The platform may be fixed, may be on wheels, or may be able to be raised and lowered. A wharf pier, a conveniently located tree stump, a concrete slab, or a fabricated steel frame may be used as a platform. In mobile cranes, where minimum weight is essential, the platform is usually made of high tensile steel, fabricated by welding. Here we see a fast production MIG welding operator working on a platform member. A typical high tensile steel composition is shown. The most important advantages of such steels are high yield strength, weldability, and low temperature toughness. The yield strength is about 3 times that for plain carbon structural steel. This derrick crane platform has a simple greased plate and pin to function as a slewing axis. Heavier slewing cranes often use a roller bearing slewing ring. The ring is machined and nitrided before use for hardness and long life. Slewing ring. To obtain the hard-wearing surface in the slewing ring, a heat-treated steel, subsequently ground to accurate size control, is required. A 0.3% carbon steel with small amounts of molybdenum, nickel and chromium is usually used in the hardened and tempered condition. The resultant microstructure consists of very fine carbide particles in a ferrite matrix. It is usually described as tempered martensite. The material has high strength and is tough. Another basic component is the jib or boom. The jib may be solid, box section, or be a fabricated 3-dimensional truss. In action, it needs to withstand compressive loading, bending stresses, and some torsion. With telescopic jibs, Teflon pads are often used as adjacent sliding surfaces. These give sufficient support and have a suitable coefficient of friction. The material used in the jib may be hardwood, medium or high tensile steel, or even high tensile aluminium. High tensile aluminium alloys have enabled savings in weight to be achieved in construction. The microstructure, 1000 magnifications, of a 90% aluminium, 6% zinc, 2.5% magnesium and 1.5% copper alloy is shown after precipitation hardening. This heat treatment process enables the even distribution of intermetallic compounds to be achieved throughout the material. The photomicrograph shows the precipitation developed later in the grains and along the grain boundaries. The particles are of magnesium zinc 2 and copper aluminium 2 compounds. To move the load up and down and to luff the jib, winding mechanisms are required. Modern cranes use a hydraulically powered spur or helical drive. The winding drum on which the rope is stored may have a grooved surface. The purpose of the grooves is to guide the rope as it is wound, and so prevent crossing of the loops. This crossing leads to rope damage. In older cranes, mechanical gear drives were frequently used. The drum was rotated by means of a crank. A pawl and spring enabled the drum to be held in a desired position. Lubrication enables the moving parts to function more easily and effectively by reducing friction. Where a tooth mesh is used for the transfer of power, the meshing surfaces are case-hardened. The lifting motion of the crane is transferred to the load by a wire rope. The rope is usually made of multi-strand, medium to high carbon steel wire, wrapped around a fibre or steel core. As the diameter of the strands reduces, then so does the carbon content. Grease is applied to assist in reducing internal friction as the rope is wound. The rope is manufactured from many small strands to improve the flexibility and to assist in withstanding shock loadings. The rope is flexible so it may pass around the winding drum, over the pulley, then sometimes through the end of the hook. As the strands within a rope become smaller and more numerous, the flexibility of the rope is increased. As the aim in wire manufacture is to produce a very fine pearlite with no proeutectoid phase, the 0.65% carbon steel to be used must first be heat treated. The steel is austenitized and homogenized at 920 degrees C, and then quenched into a molten lead bath held at 250 degrees C. This process is known as patenting, and is a process peculiar to the wire industry. After the patenting, the wire is then cold drawn to the required diameter. The resultant structure, 800 magnifications, consists of heavily elongated, modular fine pearlite with traces of fine lamellar pearlite in a matrix of ferrite. The tensile strength of the resultant material is 1800 megapascals after an 81% reduction in area from the drawing process. The pulley over which the rope passes is a most important item. If too small in diameter, it will create internal friction and premature wearing of the rope. The pulley must withstand large compressive forces. In mobile cranes, the pulley is often manufactured as a cast aluminium alloy to reduce the combined weight of the jib. Through casting, a simple method of manufacture is achieved, while the aluminium alloy gives a weight advantage. The pulley is rotated on a shaft. This is supported by bearings. Cast steel can be used for the pulley, but results in a heavier unit. The cast aluminium pulley of 99.58% aluminium would have a microstructure at 280 magnifications as shown. The grains of alpha aluminium are clearly visible and have distinctive grain boundaries. The grains have different shades of grey due to the different crystallographic orientation of each grain. The amount of reflected light from each grain is different. The microstructure also shows polishing scratches and some non-metallic inclusions. If a cheaper pulley with higher strength was required, an aluminium silicon of 95% aluminium, 5% silicon alloy would be used. The microstructure, 750 magnifications, reveals a white continuous alpha aluminium phase in massive form and in the eutectic. The eutectic matrix shows the development of silicon crystals. To hold the load, a hook or hook-sling combination may be used. For maximum strength and stiffness, hooks are usually manufactured with a trapezoidal section. Notice, the thickest section of the hook is the part placed in tension. The hook is made from mild steel or wrought iron and is shaped by drop or hand forging. All hooks are heat-treated after forging. A 1% carbon steel is often used to produce a cast crane hook. The microstructure, 500 magnifications, shows areas of cementite in a matrix of pearlite. Because of its normalized condition, the pearlite appears equiaxed. It should be noted that the cementite, iron carbide, or Fe3C, has a boundary around it and is not continuous with the cementite in the pearlite. When sketching this type of steel microstructure, the pearlite is